Hello everyone. I'm going to show how to use EDA Playground website to do some Verilog programming and simulation online. There are many online coding websites available for software like C++, Python, Java, etc. Examples of this website are the leetcode.com, Edabit, HackerRank, and many others. If you have been to some big names companies interview, you find out that they use this website during interview sessions to get candidates to code on the spot. For home users like us, we can use those websites to practice our programming skills or perhaps get prepared for technical interviews. There are a lot of knowledge and algorithms that were taught to us long time ago, but if you don't use them on a day-to-day basis, sometimes you may have forgotten them. And this website has got a lot of materials and exercise for this purpose. It is very rare to see similar website for EDA tools to work on Verilog and System Verilog. EDA Playground allow us to run these simulators for free, and also there are a lot of people know some nice example project, and those examples are very educational and informative and very fun to play with. This is the link to their front page, and I'll put the link below. Let's go there and check it out. Now we're greeted with the front page, and there are a few windows here. The windows on the left-hand side is for the test bench code. On the right-hand side is for the RTL design code. To start with something simple, we just try to print "Hello World" from the test bench. So this is the code. So, "Hello World," initial prompt, and print the message. Okay, so now I have my code and I try to run it. I click on run here, and it says I need to pick a simulator tool. So you go to the left-hand side of the screen, and there's a section in here, tools and simulators. So you expand that, and from this drop box, you pick the simulators. There are 4 commercial simulators available here. I always pick AutoDeck with Rara Pro for my project. So I choose this one, and um, let me try to run it. Okay, now it's asking me to log in. So click here to go to the login page, and there's a full access account login and a limited account login. I can use a limited account login, so I just log in with my Google account for a limited account login. So now I pick the simulator, I log in with my Google account, I run it, and then indeed we see the hello world being printed out on here. So this is the only line that is printed out from our program. The other output are the simulators when it is compiling and loading. It puts out some information there. So in order to make sure that it is running the program that we wrote, so I make some changes in here in the source code, and I expect the changes take place when we rerun it. So let's rerun it. And indeed, the printed out string in here change, which is consistent here. So it is running the program that we intend to run. So that is the Hello World in Verilog on EDA Playground website. Now let's continue with more fun stuff. So there's a D flip-flop, the data flip-flop sample on the EDA Playground that we can look at next. This is the link to go to the project directly. I'll show you how to get to this project from the EDA Playground website too. So from the EDA Playground website, I log in and then I click on Playgrounds and then you choose Publish Playgrounds. There's a list of about like 30 projects that some people publish. And on the very top, the very first project is the D flip-flop, loaded by Victor. It's got a lot of view and a lot of likes. And this is the popular project that it is fun to look at. It is a very classic design of a D flip-flop. And on the right-hand side is the RTL design of the flip-flop. On the left-hand side is the test bench. And it's pretty simple. And for the D flip-flop, we are mostly interested in this four signal, the clock and reset, like you see in every digital design device. And the behavior of the input B and the output Q is as follow. If you're in reset, the output Q is always 0. If you're out of reset, on a rising edge of the clock, the value on the input B will be transferred to the output Q after the clock edge. So very classic definition of a D flip-flop. And when we look at the test bench, uh, it's doing very minimal in here. So it set up some initial value, hold the device in reset, and then on the next time tick, it pick the device out of reset. Reset is 0. Pick it out of reset, change the value of the input D, and the value of the input D is not transferred to Q yet. Not until you toggle the clock in here. You make a rising edge of the clock in this timestamp, and then the value of D input is transferred to Q at this point. And because the original project already have this dumping the data into the waveform file, we can see the waveform after the simulation is complete. To do that, you check this checkbox here, open EV wave after run. So we check this checkbox and the waveform should be displayed after the simulation is run. So now we just run the project as is, but displaying the waveform. And if the waveform doesn't pop up, sometimes I need to run it 2 or 3 times for it to come up. So before looking at the waveform, let's see what it is printed out. So these are printed out from the test bench. So when the device is held in reset, it print out the value of DQ. And when it is in reset, Q is always 0. So it is what we expect. When you take it out of reset and change the input value to 1, the input value is not transferred to Q yet because you don't have a rising edge of the clock yet. And then on the next time tick, you generate a rising edge of the clock. So you can see the value of D transfer to Q, and the Q value change from 0 to 1 on this time tick. So it is the exact behavior of a D flip-flop. And when you look at the waveform, behavior is consistent. So it is in reset, like in this region. When it is taken out of reset, the value of D is 1, but the Q will stay at 0. And then until the clock edge happens in here, the value of D, which is 1, got transferred to the Q output after the clock edge. So it is consistent and it's behaving correctly. So how are we going to make the simulation slightly more interesting? For one thing, we're not even running a complete clock cycle yet. We have a rising edge, we don't have any falling edge. So how about running the simulation for longer with like, a few more clock cycles? And how do we do that? So we go to the test bench here, and one way of doing it is to have a procedure block in here to have a toggling clock continuously. So I do that always, and every 10 time tick, I toggle the clock signal. So clock assigned to the negation of the old clock. That means that you toggle from 0 to 1, 1 to 0 every 10 time ticks. And for that, that means that the period of your clock is 20 time ticks. So what happens if I run it? And now it seems like a simulation is hanging. Console like print out something here, stopped. And then in here, it didn't say the simulation is stopped. The simulation is still running. And I need to click on stop to stop the simulation. So why was it hanging? And this is a characteristic of a forever running procedure block. So you have a forever running procedure block, and then you get in this procedure block, the initial block is not forever, but because you have a parallel forever running procedure block. One way of making sure the simulation terminate is to have a preemptive termination command in here. So the system call $finish is the preemptive system call to terminate it. So if I make sure that I wait for a number of cycles here, a number of time ticks in here, and then I make this preemptive termination call. So to recap, period of the clock is 20 time ticks. I wait for 100 time ticks in here. So I should see about 5 clock cycles before the simulation terminates. So I'm going to run it. And then 1, 2, 3, 4, 5. So I see about 5 um, clock cycles in 100 time ticks. The simulation is still not very interesting, but at least we're running more clock cycles. So we see the toggling clock for a number of cycles. We still haven't changed the value of D and Q yet. So instead of a hard-coded uh, time tick number in here, how about like making this um, like counting the clock cycle before it finish. So if I do at pause edge clock. So for that, I'm waiting for one rising edge of the clock and then I terminate. If I want to wait for like 3 clock cycles and terminate, I repeat it 3 times. So if I run it, I expect the simulation terminate in 3 clock cycles. So 1, 2, on the third, terminate. So it is doing what I expect. So what if I want to run it for like 20 cycles? Do I repeat it 20 times like that? Yes, another way of doing it is to use a repeat loop in here. So I repeat it for 20 cycles. And I take these 2 lines out. So I wait for 20 rising edge of the clock and terminate. So I rerun it. So 1, 2, 3, 4, 5. So it's about 5 cycles here. So it's about 20 cycles in here. But D and Q is still not so interesting. So let's try to make it more interesting. So what about assigning a random value for D on every rising edge of the clock? So I assign D, U random means unsigned random number. So I have 20 iterations. For each iteration, I want to execute two things. Wait for rising edge of the clock and then change the D value with a random number. But because I want to run two statements for each iteration of the repeat loop, I need to use the begin and the end markers like so. So there are 20 iterations, and for each iteration, I wait for the rising edge of the clock and change the value of D. So now the simulation is slightly more interesting. The value of D is changing. You run it for more clock cycle, and because it is random, so you see the changing pattern of D is not uniform. But the characteristic of a D flip-flop is that the signal Q is 1 clock delay of the input D. So input D on this rising edge drop from 1 to 0. 1 clock later, the output Q drop from 1 to 0. Uh, the same thing, like, on this rising edge, the input Q rise from 0 to 1. 1 clock later, the output Q rise from 0 to 1. And you can see it like, the relationship between P and Q is 1 clock delay all through the simulation. So this is the classic behavior of a D flip-flop. That is it for my experiment with this D flip-flop project. And the code change is pretty minimal. So that's like one thing is the procedure block to create a toggling clock here before the initial block. And then at the end of the initial block, I did a repeat 20 loop in here to wait for the clock edge, change the value D, and then have a finish after the loop. So I don't feel like I need to upload my code change, and you can experiment with it pretty easily. The typing is pretty minimal. But if you would like the change the modified code, let me know and I can upload it somewhere. We talk about the full access account and the limited account real quick. Remember, I was logging on using a limited account using my Gmail login. So if you're with a company employed, you have a school or college association, you can get one of these email address. You can apply for a full access account. And with a full access account, you can access all the four commercial simulators. So it's the ORDEC with Rare Pro, the Mental Graphic, Questa, Synopsys VCS, and the Cadence simulator. You can run all four of them. With the limited account, the only one commercial simulator you can run is the audit with Pro. And that is the reason why I try to make sure all my projects work properly with the audit simulator so that more people can um, run it, experiment with it, and have some fun with it. With the limited account, you might also use the free simulators too. But what I find was that the free simulators are fine if you're doing something simple. If you're doing something more complicated or using more system core, you run into roadblocks pretty quickly with those free simulators. And also, if you're interested in experimenting with a UVM and learn some UVM skills, uh, all the free simulators for now, they do not support UVM 1.2 yet. So this is why my favorite simulator so far is the Audec with Ferrara Pro on this website. I've seen a nice finite state machine project someone upload. It's a more FSM to do the bit stream pattern matching, like matching the 5 bit like 10110, and if it match, you assert a signal to indicate a match. And I'm considering doing another video to walk through the FSM design and the code, and also expand the test bench to make it more interesting in a similar way as the flip flop. And also, when we run more interesting test case, um, we can implement a monitor to make the manual inspection of the more complex test case easier. Thanks for watching till the end. For now, stay motivated, stay safe, and see you soon.